Good afternoon to all of you. Let's start this 24th lecture of DIP. We are doing color image processing and we continue to talk about that. Hello, Saurabh. I hope you all are fresh in your afternoon. Nobody is sleeping. It's fairly late to sleep, I guess. Well, for some people, it's never late to sleep, but still, a few people are missing. Maybe I can wait for another minute before I start. So far, we have talked about color models. Last two lectures, the first lecture we took on color fundamentals, absorption of various colors by human eyes, perception, and last lecture we talked about the three major color models, which are color models of RGB, CMY or CMYK, HSI. Some part of HSI wasn't completed, so we will complete that today. We will look at the drawbacks of these color models, and hence we will look at another color model, of course not in that detail, which is also called as LAB. It's written as L star, A star, B star, but we normally simply call it as a lab color model. So we are going to talk about that as well briefly. Then important topic that we are going to talk about is a pseudo color imaging technique, what it is, how it is achieved, what people what people do in this, and that's all. So let's start with our first one, hue saturation and intensity RGB conversion. In the last lecture we had put these equations. These are the equations from RGB to HSI conversion. So if you have your color values in RGB space and if you want to convert them into HSI space, these are my equations. Hue, if it is between blue and green, then it is theta. If it's greater than green, if blue is if the value of blue pigment or an RGB, the blue axis is less than G, then it is theta. If it is greater than G, then it is 360 minus theta. I leave the for you to figure out what could be the reasons. Saturation is given by this, where min of R comma G comma B is the minimum of the three. So if G is minimum, you take that value and multiply to this ratio. And intensity is 1 by 3 R plus G plus B. Theta can be obtained if R and G are known to us, then theta can be obtained by this long equation. Derivation of these equations are out of scope, so we are not doing it, although memorizing these equations would be essential for the exam purpose. And of course, practicing them in the problem solving. So when we solve some problems, we will look at them. The reverse conversion is also possible. So if HSI is given and if you want to convert it into RGB, then you can use the formula, although the formula differs sector wise. So in the red to green sector, if you remember the color wheel, it is red, orange, yellow, green, etc. So in a red to green sector, which is around 120 degree, you get these formulae applying. I is intensity value, S is saturation value, H is hue value. H is established in theta, so cos of H, S cos H upon cos of 60 minus H, if you add 1 to it, multiply by I, gives you R. So these are the reverse calculation. These equations vary sector wise. So in this sector, it is going to be this one, and in this sector the equations will vary slightly and giving you this one. So you can see that this part and this part and this part and this part, they remain mostly the same. What is varying here is 120 and 240, etc. So these equations would be very helpful during your programming code also and problem solving as well. So let's have a small demo, and I hope that demos will work today. So remember, all we were talking are different color schemes. So I'm just going to open our favorite small little code called image.j. Use one screen, one image in image.j, and utilize it for different different grayscale values or color model values. Well, you can see that this is same as that at our background. So it will help us. I don't have to open it twice. So I'm first going to convert this, going to image, going to type, and I'm going to convert it into an RGB stack. What is RGB stack? What is a stack? RGB we are familiar. So stack is the things kept one above the other. So here the image will get split into three components. One is the red, one is green, one is blue, and it will be kept one above the other. But before we do that, let's look at the image. Now what do you think? Where is it has a strong red? So you will find that it has a strong red component here. But the red component is tricky. You last class you saw that the hue component is measured at an angle from the red. So if you are above it depends on what is your theta value. If your theta value is say 5 degree, it would still point to red color. If your theta value is 355 degree, it will still point to red color, but the hue will vary a lot in the hue diagram. If it is slightly less than 0, then in the HSI diagram hue will look very dark. If it is slightly above 0, I'm sorry, I said reverse. If it is slightly below 0, then hue will have a large theta value and it will be seen as very bright component. If it is slightly above red, then it will be seen as a dark component. So this is my red here, it will dominate. You can see that the rest of the image blue dominates. It's a predominantly a blue color. So let's go ahead and check its RGB stack. So you can now see here that here it's a red color. If you look at it, this is red. One of the three images. This is the red. This is the red spectrum. What it means is wherever there's a dominance of red, it would, and below 0, it would be seen as a very white or very bright. Wherever red is less, it would be seen as weak red. For example, this background is towards white, and white has an equal mixture of red, blue and green. So some red is here also. Very strong red is over here, so that is shown as white. There is almost no red color appearing here in these darker sections. So these darker sections are almost black in this. There is no red. What about this is red. What about the green? This is the green component. You can see that the green is not very strong here. In fact, green is not very strong at many places except at the lighter section, because remember in an RGB intensity is interwoven into your RGB values. So here it is lighter, so the green has to be there. That only can make this section so light. So the green is there in all these parts. And then finally blue, you will find that blue is a strong blue component at the distance and the horizon. So it is there here, over here. And in a very similar way, I can go to image and hopefully I can convert into HSB stack. No, it is not doing unless I reopen my image. So let me reopen file. Yeah. So now I can go to image, go to type, go to, this is hue, saturation, intensity, which is written as brightness stack, HSB or HSI. And this is the hue stack. You will find that this is red color. So you are very, very close to the 0 degrees. So this looks dark. You have a, this is bright white, close to white. This has a huge component of red. Even this looks very dark because your hue value, angle theta, is very small. So it looks almost black in these sections. But then there are rest of the images, there is some medium value of red color. So it looks some gradations of gray here. So this is gray. What about green? So you will find that, as I said, the green is almost missing here. It's weak green, so you will find it black. And no, sorry, saturation. So you can see that here it's, here very colors are highly unsaturated, very faded colors. So it's black over here. The colors are very much saturated in this section, especially in this part. So you will find that the saturation component stronger. Here the white means a strong saturation, black means a poor saturation. That's how the saturation is mapped. The third mapping is the brightness. So wherever it is more bright, it is bright. Wherever it is less bright, it is dark. So brightness mapping is nothing but your grayscale image. If you convert this into a grayscale, you anyway get the brightness mapping or intensity mapping. So that is what this part is. So you can open and see. Then finally, I will just, for the completeness, open it in the lab scheme. But as I said, we are not getting into the major details of the lab scheme of colors. This is the lab stack. This is the second and third. I will talk about it in a while before we get into this. So let's go back. This time the demonstration worked and that was great. Now, what is lab color model? I mean, why do you need another color model? That's above all. Like we already have RGB color model, we already have HSI color model, we already have for printing CMYK color model. Why do we need another color model? The answer lies in one simple fact, and that simple fact can be obtained from a very simple experiment. So at home, if you have a photo on your mobile phone, cell phone, you open it, send it to your friend, your parents, your family member, somebody who is having a phone from another manufacturer, not from the same manufacturer. Just take care of that. So suppose if you are using a, say, a Samsung phone, and if your somebody else at your home is using a Vivo phone, then send one image from your phone to his or her phone. Now try to observe the two color images by opening them simultaneously in front of you. Now when you do that, what you would precariously realize that your phone will show the image with different colors and another person's phone will show the image with different colors. If you take that image, open on your laptop screen, you will realize that the colors have changed. If you take that image, open on some other's laptop, the colors will change. If you happen to go to a mall and get into a TV showroom where large number of displays are kept, and if you start looking at them, you will find them that they differ from each other in some way or other way for the same signal that they are receiving. So what I'm trying to make sense that this simple fact or simple observational fact that different devices, they reproduce colors differently even if the coding is same, even if it's a same image, say passed through a WhatsApp compression, opening on two different mobile phones, they will appear, look to be different, the colors will vary. And this precisely happens because these color schemes like uh, RGB, etc., etc., they are not device independent. So for example, if one device shows certain maximum value of red, other device may not. It may show a different maximum value of red. And if the maximum value of red is differs, then all other components similarly will differ. Other issue is the color gamut. Remember in chromaticity diagram we had talked about color gamut. Devices have different color gamut. Typically the screens which are not so expensive, they come with lesser color gamuts, while screens which are widely with wide color gamuts which tends to be more expensive. So they tend to reproduce colors differently. Finally, if you want to print, generally the color gamut offered by the printers are less than the color gamut offered by the screen, and therefore that issue again surfaces. So there are multiple issues. So let us summarize them quickly one by one. The colors across devices can vary significantly. An RGB model or HSI model or CMYK model doesn't help at all in that. Typically, in all these cases, you have to do device specific calibration. So, suppose if I'm connecting a printer to my laptop and I want to edit an image on my laptop and print it using the printer, then I have to make a calibration between the printer and the laptop. That is my first step. So that all the color that I see on the screen, I should be assured that the printer should be able to print. Suppose I observed some shade of blue but printer does not print that, then it can become an issue in the future, especially when it is commercial printing of say billboard size. So the calibration is important, necessary to maintain a high degree of consistency between monitors and eventual output devices, as I have already discussed. So we require a color model which is device independent, which does not depend on the device value, where the same values represent the same color, same hue, same shade, irrespective of what devices you are using. So one such color model that has been developed for commercial work is called LAB or lab color model. But as I said, for our purpose, particularly for DIP purpose, it is not of much importance. It is needed whenever there is a printing is involved or cross platform transportation of images are involved. Color lab color model is calorimetric. That means color perceived as matching are encoded in very similar way. Then identically perceived uniform. So it is very uniform color model, or it is identically perceived on all the devices uniformly, and it is also device independent. Let's go to the next part of today's discourse, and that is pseudo color imaging. Now, with this lab introduction to lab color, I think we are done with the major color models. Most of the time, you're working, even CMYK, we will not be very, uh, we are not going to use much. Most of the time, your working will be either in RGB model or in HSI model. So remember those equations are important. Converting from HSI to RGB and back. Of course, conversion from CMYK to RGB is not challenging. So you may remember it. CMYK typically is used for printing. If any one of you want to, suppose you are working on your computer for an image to be printed or to get printed, then change the color space to CMYK and then work. That's the advice. Then going to the pseudo color imaging. Pseudo color imaging is very important. Let's look at this picture. This is a grayscale picture of, I guess, thyroid gland. And you can see that this is a decent image. Some shades of gray, black. However, to assign or to extract more information from it, or to make it look more appealing, we can convert into color by assigning color arbitrarily like this, or maybe by using some scheme, as I will come to it. So here what I'm doing is I'm applying some arbitrary colors. How many colors I have chosen? So you can see blue, orange, green and yellow, or is a blue, orange, green, yellow and red. So five colors I have chosen and I have assigned it to it. And you will find that moment I do that, here the boundary which was hidden in the background has now come up in some color form. So this color is, this kind of color redemption or coloring a grayscale image is called pseudo color images. Well, why is it called pseudo color image? Pseudo, something which is not real, something which is imaginary. So we have not seen the object, we have not seen the exact color of this object, but we assign color according to our own convenience. I will give you another example here. This is a grayscale image of a man who is drinking some cold drink, and this image has been clicked using an infrared camera. Now you know that the infrared camera shows some sort of correlation with temperature. So I can use a color scheme which can represent temperature. So maybe I can use warmer, brighter colors for the warmer parts and cool and dull colors for the colder parts. So I can convert it into this way. So you can see that the body is at a higher temperature. So looks red, other colors recedes, and finally blue purple will appear over here. So this is another pseudo color rendering, but here the colors rendering has a purpose. You have a scheme here. So it can be done with scheme and without scheme. Another example I would like to uh, tell you is that old images, old movies, old Bollywood movies or Hollywood movies, as you know, many of them are now being colored and reproduced. So again, you use a pseudo color imaging technique there. Just that you have to have some plan, because you cannot make a skin tone look yellow or red. It has to be of the skin tone. So with some scheme, using pseudo color image technique, you can convert an old black and white photo of your grandparents and others into a color photo. In fact, for many students, this kind of project has been a favorite project for DIP. Going ahead, so how do we do it? So let me present the basic scheme of working, and then perhaps with one or two more examples, we can end this lecture. So what basic scheme we use is something called as intensity slicing. We have already learned intensity slicing in some other chapter, in some other context. It is coming back over here. So suppose if I have my X and Y image plane, XY is my image plane. Some object is depicted in the image plane, which has an intensity graph which is plotted along z-axis. So my intensity, which is nothing but f of xy, is plotted along x-axis. The darkest spot in the screen or in the image is 0. The brightest is L minus 1, which is white. And you can have a plot of intensity versus position. What it is trying to show you that I have a blob here and I have another blob. This blob is somewhat white, because somewhat bright, because it has a some little less gray. This blob is very much bright. Okay, so now intensity slicing comes into picture. You slice, take one plane, intensity plane. This is one intensity plane. Now once I've chosen, I know that only this part, it only cuts through this part, only this part of the image is in this plane. The rest of the image is not in this plane, it's below, only this part. So now what I do is I will assign a color to this intensity plane. Suppose I assign red color. You can assign red color to this intensity plane. What would that mean? It means that this part of the image will get red color. Remember, not the whole image, because it is not intersecting the image anywhere else, only this part. This will get the red image. So different color is assigned to each side of the plane. You can go, say, suppose if I keep the scheme simple, I would say that all the intensity values which are above this plane gets, say, color 1, and all the intensity values which are below this plane, they get the color 2. So different colors are assigned to each side of the plane. Once you do that, then you have created a two-tone pseudo color image. So for example, everything will go as a background and only this part would be shown in some different color. So everything can be assigned blue and this part can be assigned yellow. So it will look brightly on blue background. So that is the way to do it. Remember, the color assignment can be arbitrary as we have seen in one example, or it can be planned as we have seen in the other example. Now, how much of the image you want to be yellow, for example, in this side of the plane, that can be decided by shifting this plane up or down. So you can go up in this intensity plane, you can go down. As you go down, remember it will intersect more and more area. Eventually it will intersect here also and here also, and then you can assign two different colors. In fact, to different planes, you can also assign different colors. Even that is possible, and I'm coming to it. So this is the way you will achieve your pseudo color imaging, two-tone pseudo color imaging. This is the another way to write that my intersecting plane is at Li, L intersection. So all the levels which are below this, they have been assigned the color C1. All the levels which are above Li, they have been assigned the color C2. So yeah, going ahead. Now, instead of applying only two tone, three tone, or five tone, you can also apply a continuously varying color assignment, continuously varying spectrum. How can you do that? Very straightforward. Suppose this is my original image, which is in grayscale. Remember, these kind of images we have seen a lot in our geography books. This could be in the part of clouds or rainfall or whatever. Now, I want to convert this into a pseudo color image. How do I do it? Very straightforward. I introduce a key here. So in this case, a color key can be introduced. This is my color key. How does it read? It says if the intensity is 0, you assign this end blue of the spectrum. Then as you go from 0 to 10, so you can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you assign to different intensity, these are my colors. Between 10 to 20, you assign these as colors. About 20, you apply this bright red color which is on the extreme right. And I do that. So this is my continuously varying color assignment. Okay. So you can divide it into small thin steps and you can assign each intensity level as one color band. And then you apply this to get your result. And you would find that suddenly the data becomes more appealing. Suppose I say that the temperature is high in this region and in this region and in this region. It might show temperature, might show rainfall, whatever. So this side could be high rainfall, this side could be less rainfall. So these are the regions where the rainfalls are high. So you can vary this as well. Okay. So That is how your pseudo color imaging goes in a continuous domain. Typically, you take your original image, you convert it into RGB stack as I had demonstrated. Then you take each stack and then according to the scheme, any scheme that you choose, you assign, you do a transformation. You assign to take the red stack, say my these much this much to this much red value will get this color and this to this will get some other color, and then you convert. Remember this, I'm talking from one colored image to a pseudo color image. I'm not talking about a grayscale. You take a color image, convert it into a stack, convert each one of them, process each one of them, and then finally get three processed image. You can merge them together to make one resultant image. This is how it will happen with a color image also. So you have one color image, from there you produce a pseudo color image. Finally, I would like to end this lecture with this image. It's a beautiful image which I found from the reference. Jupiter in false colors, and you can see that how those spots on the Jupiter surface have been exemplified using false color imaging technique. Remember, Jupiter will not look this way if you use a real color imaging technique. So we end this lecture with this. Thank you.